Welcome everyone to the week 11 tutorial session of Algebraic Combinatorics MA19 2023. Today we'll discuss sample assignment related to week 11. And yeah, I forgot to tell, I'm Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. So let's begin. Okay, so this is related to how we can if we insert any number like let's say a to p, then how will it behave and how the type will change and these things. So this is mainly related to how RSK work. So let's begin. Let p be the pb of type 4321. Okay. Yeah, so P is a semi-standard young tableau. So which is of type 4321, which you can see this is 4321. So this is the type. Now if A is equal to 3, then how what will be P inserted by A? Okay, so let's see. Okay, I can copy this. Sorry. Okay. So yeah, so this is our P. Now what we need to do, we need to insert A is equal to 3. So we are inserting, so how we will start? We will start from the first row and how it will behave. So let's so this is 3. So if you insert 3 in P, so how it will behave? 3 will be, so we'll first search for, or maybe like for the first row maybe, or any row, search for or maybe, okay, if we number first row as A1, A2, or as we name first row as A1, A2, A3 up to and so on, whatever it is, let's say AK, then we'll search for AI, least I, search for least I such that A is less than AI. Okay, so we'll start from the first element of the row, and then we'll look all the numbers and we'll search for such AI such that A is less than AI. So now here what can you say, like which number you can consider now for such a, which I you can consider here, or which AI you can consider? So here we are looking for, so there is 1, 2 and then 3. So AI is strictly greater than A, so that means we are inserting 3, so that means 5 is the only choice, and we are searching for the least I. If, like for example, if it would have been 4 and 5, then we will search for 4 only. Okay, like the least one, which least I such that A is less than AI. Okay, so what we will get? So here just replace 5 by 3. Okay, is that clear? The first row is now 3.
Yes.
1 2 3 3. Now we are inserting 5. Okay, because 3 is 5 is replaced by 3 and 5 is free now. Now we need to insert 5, that we will do in the next row. So we have to insert 5 here. Now the same process we will do, so it's not particularly for any row. So you can just say if we name each row as this, any row maybe. Okay, So now what we will do, if we, so this is the thing. Now what we will get, let's see. So when we insert 5, now which number we can take as AI? We again need to do the same process. We need to, so A is your, so now this is your A. Now you are inserting 5 in this row 2 3 6, and what is the process say? You search for least I such that A is less than AI. So which number you can replace now?
6.
6, exactly. So you'll just, because 3 is less than 5, 3 is less than 5 and we need the bigger number. Even equality won't work. We need bigger numbers. So 6 we can be replaced by this. Will be replaced. So now 6 you will insert. To insert 6, again the same thing. What will we get?
3, 6.
Yeah, exactly.
Next is 7.
Yeah. So yeah, this one is 3. So yeah, as you said, we'll get 6, and this is 5, this is 3. Now 7 has been replaced by 6, so 7 need to be inserted here. Now what will we get? Next step, same
7.
thing. Yeah, but now okay, so right, so what will we get here? This will be replaced by, right, 3 5 6. Now here this will be 7, and now 8 is free. So where 8 will go? 8 will go in the next line, right? So 8 will be here. Is that okay? Yeah, okay. Yeah, just a thought. Okay, cool. uh, right, remember, this 7, the box will not come here, because for example, if at the place of okay, let it be. So this will be this, because I just trying to have an example for other thing. For example, if 8 is 4, then the box will be here. If the box will be here, then it will hinder this thing, like this will not be a tableau. So that's okay. Okay, so we'll get, we got this tableau. So this is your P inserted by A. Is that clear?
Yes, ma'am.
Okay.
But the second question is what is A? So how do we find? Here, madam, in this question, A we directly give.
Yeah.
Question is we find to A.
Find A. Actually, next question is related to that only. Now, let's see the next question. So let P be a semi standard young tableau of shape 4422. It is given that for a positive integer A, P inserted by A is of this kind. Then find A. Okay, let's do that. First thing, uh, you must, you must have what exactly is P, like how exactly P look like, because as you can see 4422, if it is given that 4431, then the process will change, because it could be anything, because there is just one extra box, we know that, but we don't know where it exactly is. Okay, so for example 4422 is also okay. P could have been 4431, right? So this is like 443 and 1, like maybe this box is here. Okay, so we don't know that. So whenever it is given that P inserted by A is this, then you must have what exactly is P. Okay, so only that you can find A. there could be possibilities where this is not the case. For example, you cannot have 3 4 2 2, because you know that it should not be like that, because it should be in the horizontal thing. So 3 4 2 2 is not a possibility. This should be in like not strictly weekly increasing sequence, so this is not a possibility. So if such kind of possibilities are not there, then they might omit what p looks like. Okay, so for example, here there were the possibilities. So for example, if you have given, for example, I'm just saying, if you have given 4 comma this is for example, this is your p in pa, then p must be of the kind 4 comma 3, because it cannot be 3 comma 4, and there is one extra box that we know for sure, right? So at this like at such kind of questions, they may omit what p looks like. Is that clear?
It's not.
So, if there is a discrepancy, then we should know what exactly the P is. Like, what is the type of P? So let's see here in this question what is happening. So this, okay. This is yeah. Now you know that P is 4422 type uh, of the shape. Sorry, not type. These are two different things. P is of type 4422. Then there must be like this part only. This must be the extra one. Okay. So let's start here. So okay. So what I'll do, I'll remove this, and now 4 is b. So you are going reverse reverse the process of inserting a, right? So what you are doing in the process of inserting a, what you are doing, you are finding some ai such that a is less than ai, right? Now what you need to do, you need to like reverse this process. So this is your ai. Now you will search for such a, and this I was the least number, least in that row, right? So what you will do, 4 is behaving as ai because that has been replaced and that has been inserted somewhere, right? Yeah. So one second. uh, yeah, that's all right. So 4 is equal to ai. Now what you need to do, you need to find such a, or maybe in the previous step, such a such that a is less than ai, and I is the least one. So that means, so let's see. So for firstly look at such ai which is less than such a which is less than ai, that means which is less than 4. So that means you are looking at these three elements. Okay, now in the process, what has happened, now think about what would have been like what would happen that time when you inserted a. Then ai will be replaced by a when ai is bigger than a. Okay, so you are with 4. Okay, now when you insert that, you will look for the highest, like now in the process, now you will look at the highest one, which is which is nearer. So what I'm saying, you will look for such a such that a is just less than ai. Okay, now you will so the nearest one. So what you will do, this 4, this 3 will be replaced by 4, and 3 will be here. So now what you have done, so let's now look at this point. When you inserted 3, 4 would have been removed, right? Now think about 3 as a. When you have inserted 3, 4 would have been removed, replaced by 3. right? And this happened, so we are just reversing the process and we are writing in the form of a only. So this is equal to what I wrote earlier. Okay, so 1 2 2 4 2 3 4 5 3 4 4 5. So here this 3 is this, and now 4 must have been inserted here. So is that clear, this part? Just reverse the process. Now reversing the process, you can always tally. So what you are doing, you wrote the equality, or maybe like, so this 3, when you insert 3, 4 will be removed, you will get 2 3 3 5, and you will insert 4 in this row. And this is exactly the reverse process we are doing. Okay, let me complete this, and then you might understand well. So you have this. Now again what you will do, so this is, now this is 4. Okay, and this have been removed. Now 3 3 is has been inserted here. Now again what you will do, 3, you'll take it to the previous step. So what I want to say, when you have inserted 3 must be coming from the previous line. Okay, now in the previous line when you inserted some number, what would have been done, like if you when you inserted some a, then you must have looked for this, and this ai will went to the next line. Now what is ai is 3. So you are looking for a such that a is less than ai, and I is the least number in that sense. So the replacement have been done at this place. So what I want to say, uh, like here at this point, so you are looking at a number which is strictly less than ai, like, and which is nearer to ai. So what I want to say, uh, this 2 will be replaced by 3. um, so again this is 4. So this is 4. I'm saying you must have inserted 2. So think about it. So this 2, when you insert 2, you will get what you will replace. You will replace 3 by 2 when you insert 2 as a. When you insert a to be 2, then 3 will be replaced by 2, and 3 will move to the next step. And when you insert 3 in this row, in the second row, when you insert 3 in this, what you will get, 4 will be replaced by 3, and 4 will move to the next line, and that will come here. So what I did exactly reverse to that process. So is it somewhat clear?
Yes, ma'am.
So
Clear, ma'am.
what you will do, just what in the process, what you will do, you start with the extra element wherever it is, which this shape will tell you. So from the shape you will figure out what number has been added to where exactly the box have been added. Now from that box, yeah, right, from that box you will you start with that box, and then you add that box to, sorry, yeah, so you start with that box and add that box to not box. So what I want to say, that number, that 4, you will from where 4 has been uh, 4 must have been replaced, that you need to figure out. Okay, so from the second row you look at the when 4 will come out, so when a is less than ai, from there ai is your 4. So what you will do, you will search for the lowest number, not lowest, uh, what I'll say, a number which is less than 4, and there is no number, no places in between. So what I want to say, this 3, I'm not saying this 3 have been replaced. Okay, this 3 will not be replaced, because anyway this is the bigger number, that cannot be a possibility. So you will look for the number which is just less than 4 in terms of the place. Okay, so you will look for that element. So 3, and what you will do, you'll replace 3 by 4. So you must have inserted 3 in that row, that is from when you inserted A. Now 3 will be replaced by 4, so you'll get 4, and this is your, you must have inserted 3. Now you go to the first row, and again you do the same process. You search for the number which is less than 3, and the place is biggest, whatever it could be. So 3, now in this row these 3 numbers are lower than 3, and then you consider the biggest one, like biggest in that sense, in terms of place. So 2 will be replaced by 3, and you will get, you must have inserted 2. So this is the process, and you can check again, like so when you have inserted this, so 1 2, now when you insert 2, then 3 will be replaced by 2, because that is the a is less than ai, and I is the least number. So you'll get 2, and here 4, and then you will insert 3 here. That is the next step. So next step, when you insert 3, you will search for such ai such that a is less than ai. So this will be 3, and you will insert 4 in this line. And as you can see, 3 and 4 are already there. There is no number which is bigger than a. So you'll just insert a new box, and you will write this. So this process is easy to see, but when you go back, what you will do, you will just reverse the process. So what you will look for, you will look for the number which is just less than a, and the position is highest possible, the in terms of like a1, a2, a3. So you'll search for the biggest number, biggest number I, such that ai is less than a. That is very bad to say, but whatever number has been inserted, you will search for the nearest one. Is that clear, or should I
Yes, ma'am.
consider more example? If you want, I can
No,
consider.
ma'am.
It's fine. Okay. Okay. Yeah, you will see in RSK thing also. So there will be more in this also, because RSK of A again consider this going back process. So we'll see. Okay. So A is given to be 201111. So what is RSK? RSK is the bijection, this okay, not A to RSK A. This is equal to this P comma Q, where P and Q are, one is insertion tableau and Q is recovering tableau. How we get that, you can see in the process. So A is this. First consider the bivector. What is bivector? This actually tells you what exactly is A. Firstly, A should be what? A should be a Z plus matrix. Z plus means even zeros are allowed. So you can have any natural number, and natural number we always considered with 0. Okay. So any so this is this integer matrix. So entries are from the set n. Okay, now how bivector will be written? What you will do, it will not consider zeros, but whatever non-zero entry you have, it will write it in a form. So what I mean to say, so firstly move row wise. Okay, so first move to the first row. Now what you will do, you will write this number. So you write the position of this number. So position means this will tell you the row number, and this will tell you the column number. Okay, so 2, what is the position? A11, that means the first row and first column. So this is the position. And the number 2 says, so why we are only allowing n, we, so that we can write something of this kind. So 2 is what? 2 means you will repeat this entry by like you will write this entry twice, so that it will tell you you have 2 rows of like the value, sorry, so that you will know you have the value 2 for this entry. Okay, so you repeat it as many times as the number is given. Okay, is that clear?
One more time.
Okay, so what we are doing, so how we are writing the bivector, so you consider you move around rows. So we will see the first row, second row. So we are at first row right now, and what we will do, we will write, so this first entry, let's see this first entry. 2 is what? A11. A11 means first row, first column. So what we are recording here, we are recording row, the number, the row number and the column number, and the entry will tell you, the value of that entry will tell you that how many times you will write that. So the recording is what? We will write it twice, because the number is 2. So if it is 3, we'll write it 3 times, and like 4, then we'll write it 4 times, and if it is 1, we'll write it only once. Okay, for example, for the next entry is 1. Okay, and the row number is 1, column number is 2, because this is the second column, and we will just repeat it one time, because we know that this is the number has been written only once, like sorry, the entry is 1. So the entry will tell you how many times you will write it in this bivector. Okay, I will not write 1 2 again, because that means the entry must be 2. So this corresponds to A11, this corresponds to A12. A12 means in terms of the matrix, if you consider the matrix to be of this kind, A21, A22 and A23. Okay, so in that sense we are writing. So for example, can you tell me what will be A13, because we are going row wise, so we'll complete first row first and then second row. So what?
1,
1
3.
1 3, exactly, and we will just repeat it once because the number is 1. And now next, will
2,
be
1. 0.
oh yeah, so 0 means the number of times you will repeat that entry, or maybe the recording, only 0 times. So that means it's just it won't be considered. So 0, for 0 you will not write anything, because this tells you how many times you will write it, and 0 means you will not write it. So we'll not record anything from this. So next will be just next number, that will be what?
2, 2.
2 2, and this will be repeated just once because the entry is 1, and the
2, 3.
next 2 3, exactly. Okay, so 0, so the one thing is in this RSK thing, that if for example a would have been 2 1 1 0 1 1 and 0 0 0, for example, then the same bivector you will get, because it does not record 0, it does not consider anything related to 0. So if you have extra 0 row or extra 0 column, then it will not record anything. Is that clear? So if it comes in between, for example, if it comes here, then it will get recorded, because you know that this entry will got 3 1. So this entry will be A13. If this would not be in here, then it will be A12, right? So that will be considered, like if it is if you have any zero row or zero column in between. In between means something after that there is some 1 2, any non-zero entry is there in the next row or next column, then it is okay. Otherwise, if you have just zero entry out at this place, so for example, if you have this, I'm saying with this A, so what I did, I just added one extra row with zeros only. Okay, so the bivector of this one also is same, like of this A dash is same as bivector of A is same as bivector of A dash. Similarly, if you add here 0 0 0, you will there will be no difference in terms of bivector. Is that clear?
Yes, ma'am.
But if you add something out other than 0 now, then it will be considered, because the row number will change, like the column number will change for these things. So it will tell you there are 5 rows, sorry, 5 columns. Okay. Now so this is the first step. So now you know the bivector. Now what you need to do, so okay, I'll write bivector in the next page maybe, because you need to see again and again. Okay. So this is the bivector we got corresponding to A. Now we need to find out RSK of A. That means we need to find out P and Q. And what are P and Q? P and Q are, P is insertion tableau, and Q is recording tableau. So what it does, so let's see what we will do. We will consider, so what we will do, we will insert these numbers, the numbers which are in the second row, that means the column numbers. We'll insert these numbers one by one, and then we will record it like where at which place we did. Which place means these numbers, we will record these numbers, and we will insert these values, and we'll record it by the row numbers. Okay, let's do that. Oh, okay. Okay, let's do that. Now we'll start with, firstly there is nothing, so it's just 5, because there is nothing. Now we will insert, and corresponding to 5 we have nothing in the recording also, because there's nothing. We are again getting the tableau. Okay, so we are again getting the semi-standard Young tableau. Now so we are now inserting 1. Okay, as we inserted A, we will do the same process. So how we insert any number to any tableau, we will do that process here. So we are inserting 1, and when you insert 1, you will just, because there is nothing in the first row, you'll just add it in the first row. First row means that is the only row right now you have. Corresponding to this one, the recording will be done in terms of the row number, so you'll get just 1. Okay, so one. I write the both one, so I'll try to be uniform. But okay, this and this same as one. Okay, if you have confusion, just let me know. Okay, so this is one, this is one. Now, so what I'm writing, that the thing we the tableau we got, I'll write according to that, and then I'll write insert. You insert now the next number. Next number means one, so you insert one. Okay, so yeah, when you will insert one, what will you get? One. When you insert one, what will you get?
One, one,
One
one,
one.
one.
Right, because there is no ai which is bigger than a. Okay, so if that is not the condition, then we'll just add the extra box. Okay, so 1 1, and then on in the recording side, what will we get? 1 was already there, and the row number is 1, so this is 1. Okay, now you insert the next number. Next number is 2. So you insert 2. Again, the process says when we are adding a, so if a is less than ai, then we will replace it, otherwise we'll just add the extra box. So you'll again add the extra box, and the corresponding to that, the recording will be in terms of the row number, that is 1. Okay, is that clear till now?
Row number one. Ah, yes, ma'am.
Yeah. So now next part, next number is 3. You need to add 3. So again the same thing, because there is no number which is less than uh, like which is greater than 3. So we'll just add the extra box 3, and corresponding to that you will get 1 1 1, and this number, that is 1. Okay, we are just recording the new number exactly there. So this recording is basically you will write the row number wherever the extra box has been inserted. Right now there is no issue because it is going parallelly, but in the next step, when the replacement happen, then you have to think about it clearly, because recording will be doing. So what recording is doing, wherever you are adding the extra box, you will write the row number there only. Okay, not at the replacement place. You can see later. So for example, next step is 2. Now there is something which we need to be careful right now, because there is a number ai such that a is less than ai. That means 3 is there which is bigger than 2. So that means 1 1 2. Now this will be replaced, 3 will be replaced by 2. And where 3 will go? When you insert 3 in this, 3 will go to the next line, because what you will do, so in the first row 3 has been replaced by 2. Now 3 has to be inserted, so in the next row we have to move, so that is 3. So you'll get this. When you insert 2 in this tableau, then you will get this. Is that clear?
Yes, ma'am.
Now see, corresponding to that, 1 1 1 1 will exactly be like that. Now wherever the extra box has been inserted, that is this 3, at this place you will write the row number, that is 2. You will not replace at the place of wherever you have inserted in the first row. Wherever the extra box has been inserted, you will write the row number there only. Okay,
Yes, ma'am.
now the next one is you insert 3. So you'll insert 3. So in the first row you can do that, because it's already, because there is no ai for which um, it is less than or equal to. So you can just insert 3. So you will get 1 1. You have inserted the, so you'll just write the earlier one, and then wherever you have inserted the box, that is here, you will write the row number, so that is 2. Is that clear?
Yes, ma'am. Ma'am, we insert two now. 1 1 2 3. Insert two. So
uh,
there we can 1, 1, 2, 3, 2. It's possible, ma'am.
I didn't get it. What exactly you're saying?
1, 1, 2, 3. Insert 2. So the next step, madam, write 1, 1, 2, 2, 3.
Huh, right.
So 2, 3. 2 is possible or not?
uh, so what we did at this step you need to
Mm.
insert 2. Now what you will
Mm.
do, you will start with the first row. So there is a tableau. Now you're inserting 2, so you have to do the full process, this first row, second row, full process. Now
Mm.
what you will do, when you see there's just one row, so when you will start with first row, and then first row says you have to replace 3 by 2, because there is a number ai such that a is less than ai, and I is the
Mm.
least in that sense. So that is the only thing we have here. So 3 will be replaced by 2. So you got 1122. Now whatever number you got, okay, so what we are doing, 1123. So this is not, this is the full step we did. We are not writing the steps of inserting. So you are
Okay.
inserting, this is your p. Now you are inserting, so I should not write like this. There's a these are boxes. Okay, you are inserting 2 here. So what will you get when you will
1,
insert?
1.
Huh. So you what you will do, this is your tableau. This is 1 1 and 2, and you know that there is a ai which is such that a is less than ai, so you'll replace that. Now you have to insert 3. So first row is over. Now second row you need to insert 3, and there is nothing, so you have to just insert 3, because you what you need to do, in the next step you need to complete that, right? Because there is nothing to check.
Mm.
So you will get this. So this exactly I wrote. And in the next step, when you need to insert 3, this is your p now. Okay, this p.
Yes.
Now when you need to insert 3, so first row says you have 1 1 2 2, and now there is no ai such that a is less than ai, so you have to just insert the box here in the first row itself,
Mm,
because in
I
the
got.
hmm? Is that clear?
Yes, ma'am.
Okay, so this exactly I wrote here. And wherever you are adding the extra box corresponding to so at that place of extra box you will write the row number in the recording tableau. So I did that only. Okay, so yeah, so you got so this is your p, and the process stops here. 2 2 3, and this is 3. Or maybe you can write, this is your p, this is p, and this is q. So RSKA is P comma Q. So this is this, and 1 1 1 1 2 2. You can write it in the form of this also. So this is your P comma Q. Okay?
Yes, ma'am.
Okay, let's see the next question then. This was asked here. Yeah, find RSKA. Okay. Yeah. Let's see this. Let a is equal to, now same thing, we are again trying to write what is RSKA, and here also we have to verify the process. Verify as in the reverse process. So this is a bijection up to up to 0 rows and or columns, because you know that the bi vector you will get corresponding to a does not look at the 0 rows which you have like in the end. Okay, I should write 0 rows or 0 columns in the end, or something like something related to that. So in the end means as I explained earlier, so you can get something, you are not sure if this is your A or something else. Okay, so this could be your A also if you go the reverse process, because you know that when you got the bivector, it does not record this thing. So you are not sure unless you know what is the size of the matrix n cross m. If you know the size of the matrix, then you are okay. So for example, a reverse process, assuming, or you can write, so this part up to this, and that, that is assuming, not that is, oh okay, it's fine, or assuming the size of the matrix to be 3 cross 3. Okay, so if you fix the size, then there is no issue, because if there cannot be zeros, because you know that you will get something like this. And for example, if I say the size is 4 comma 3, then you will get something of you can add extra zeros in that case. Anyway, but like if you fix the size, then the only possibility you know is exactly that. So okay, so let's start. Again the same thing we'll do. A is given to be 1 2 0 0 0 2 1 0 0. We'll consider the bivector. So can you tell me what will be the bivector?
1 1
1 1
1 2 1 2
1 2 1 2, exactly.
2 3 2 3
2 3 2 3, very good.
3 1 1.
3 1, exactly, very good. So this is the bivector we have. Now again the same thing, we'll try to find the tableau corresponding to this. P is given to be insertion tableau, and Q to be recording tableau. Okay, now let's start. Again we'll start with 5. There is nothing in at first. We'll insert the first column thing, like column number. So we'll insert 1. So when you insert 1, you will get 1, and corresponding to that you will consider the row number, that is 1. So wherever you have inserted the extra box, you will write at that place the recording number, this row number. So 1, and here you will get 1. Next step, we'll insert 2, right? I'm inserting 2 now. So you will get 1 2. Extra box is in the first row, second column. So you will get the corresponding thing to be this one. So you'll just write 1 1. Next, okay, I hope this is in the same row. One one. Now next step, you will insert 2. Okay, you will get 1 2 2,
2
and corresponding to that 1 1, and here
1
row number 1
and 3
3, exactly. So you'll insert 3. So 1
2 2 2
yeah, because again you don't have the condition A is less than A, so same
1
thing. 1 1 1 2.
2 again 3
Again 3, right.
1 2 2 3 3 3
3 3, just 3 3, no, 2 times, right. You will get 1 1 1 2, and next number is 2. So I'm just trying to make the box or line so that we'll know at which step we are.
Next you insert 1.
Now we need to insert 1. Yeah, now
1
what we
2
will get,
3
sorry,
1 1 2 3 3
exactly. And
2
where? Next row.
Down. 1 second.
Yeah, exactly. Very good. And now you have inserted the extra box here, so you will write the number at that position only. So that is 3. Okay. So the process stops. So this is your P and this is your Q. Okay. Now, so what did you get? RSK of A is equal to P comma Q, and which is what? Which is 1 2 1 2 3 3. So 1 3 1 1 2 and 2. So this is your P comma Q. Now what we need to do, we need to find out, now we need to do the reverse process. So reverse process means you are trying to get the value of A again. Like what you are doing the exactly. So right now you have inserted the number. At each step you need to find out what number has been inserted. That is exactly A you need to figure out at each step. So this is again the reverse process. So let's try to do that. And what exactly Q was the recording number. So recording number will be in the first line, and the numbers which has been inserted will be in the second line. That is the column number, and the first line is the row number. So basically you need to find out the bivector. Okay, let's do that. Okay, how shall I start? So yeah, I can write like this. So we need to find out the bivector. Okay, so what we are doing, we are going from the we are going like this when we constructed P and Q. Now we need to go like this. So we have to start with the last column in the bivector. So, okay, so consider this 1 1 2 3 3, and here you have 2, and here you have 1 1 1 2 2 and 3, right? Now we need to write the bivector. Bivector is the last box you have inserted, that you need to find out. So where exactly you inserted the box, that is something you need to find out. So first thing, okay, can you tell me which box has been inserted in this? Can you find? By looking at these two things, you know how we have constructed it, we know the process, so we know how. So yeah, tell me, like which row must be the last, like which box has been inserted?
First column is first row 1 1.
So what we are
It is 1.
so what I'm saying, so in first row is Q. So this is your Q, this is your P. So first row will tell you which row number you are in, and when we wrote the bivector, we went from first row, second row, third row, like this only. So what does that mean? Yeah, what I was saying, 1 second. Yeah, so what I was saying, uh, oh right, yeah, there were 3 rows. Yeah, the question was with 3 rows, right? So first row, second row, third row. Okay, so what you will do, so if the row is 0, then you don't know anything. So we are not considering the fact that the row is 0. Any last row or last column is 0. We are not considering that. So the last row must have something non-zero that we know, and uh, Q considers the row number. Okay, so we know that the last number, the biggest number in Q is 3, right? That means that must be the last one. So and there is no other 3 in this. So the only entry, or there is just one entry which is non-zero in the third row, because there is just 1 3 here. So what you will do, so you have 3 here, and corresponding to that, this is the extra box we added. Okay, that says the position of the extra box, like, so that means this number. So as I said, if you want to figure out what A has been inserted, you must know what is the type of P, right? What is the shape of P? I started with that. You must know the shape of P. That's why Q is important, because that will tell you where exactly the extra box has been inserted. So if you remove that, you will understand that was your P, and then you have added some A. So that means this position tells you that this number, this is the extra box we have added when we inserted A. So the actual one must be, so you will go the reverse process. So that number is your AI, and it must have been replaced from the first row, right? Because this is in the second row, you will move to the first row now, right? Now in the first row, this is your AI. You will search for such A such that this AI is your 2. You will search for such A which is like again nearer to AI, nearer to 2, like, but it is less than the biggest. So what I will look for, so these are the numbers, not these are the numbers which are less from this 2. So that means you will consider the biggest place where it is. So this is this one. So you must have 2 here, and you must have inserted 2. So this must be the previous step.
Yes.
Is that clear? Okay.
Hmm.
Okay, so now you know that at just the, so if you want to number it, you can number it. This is first step, second step, third step, fourth, fifth, sixth, and seventh. Okay, so seventh step, so you know that how you got sixth step. Sixth step was 2 2 2 3 3, and you have inserted 2, and corresponding to that you got this. So you know the sixth step. So that means when you know this, that means you know A, that will be your value, right?
Yes,
Oh,
ma'am.
sorry, why I wrote 2? Oh, 1 will be there, no?
Insert is one.
Yeah, one was introduced, and 2. Sorry, I wrote correct.
One,
Here
two,
must be
one.
2, and yeah, 1.
Yes.
Yeah. So that is 2, right? But 1 was inserted. 1 was inserted, that means the value was 1. So you know the value now. Okay? So you know this. Now you know the last row. Now you have to do for each step. And it's easy here because you just have one row now. So yeah, that was pretty, like, compared to like the harder ones. So this sixth, now you need to figure out the fifth step. So fifth step says, like, now you forget this. Now you are searching for now you first search for the extra box, and you know that extra box must be at the end. So this must be the extra box, right?
Yes, ma'am.
That is always at the end. So you have now the extra box 2, the row number, and this was the number that must be inserted, and this is in the first row. So there is no issue, actually you can just retrieve directly now. So you have 3. Now next step is this one. So that is corresponding to this. So basically you got 2 3, and then 2 2 1, and 1 1 1. So you got 1 1 1 and 2 2 1. So there is no issue later on, because it's just first row, and there was no replacement because the extra box is at the end, right? So you just consider the number, and that must have been inserted. But you got the how we got 7 to 6. That was important because that will give you the idea. Is that clear?
Yes, ma'am.
Okay. So you got this bivector, and now you can check was that the actual bivector. And what you need to do, now let's calculate a directly now, because you need A, you need the matrix. So
Yes, ma'am.
corresponding to that, what you will do? to find A, this is your bivector A.
2, 2,
Yeah.
0.
So yeah, first 1 1 means first entry first. So A11 is just, and it is repeated once, so that is 1. Yeah, and first row second column, yeah, that is 2,
2.
and 2 3. So 2 3 we can write second row third column, that is 1. This is oh,
Third row column.
so second row third column, the same one, no?
Yes, ma'am.
So
2, 2.
yeah, right.
Third row first column 1.
Yeah, 1, and others are just 0, right? That was the matrix. That was the matrix. Is that clear how we retrieve back? So the only thing you need to find out how we exactly get back your A, like how we do the insertion and then know the number which has been inserted. So that is exactly we need. Okay, so there is one more thing I think where you can get stuck. So when you do this process, there is a possibility. For example, I'll change the color. So for example, at this place you have this. Okay, for this. Okay, now you know that the third row is in the end, like you must have third row number, but where exactly, this one or this one? You don't know. When you were doing the, like you have, this is your queue, for example. And 3 is there in the first row also, and in the second row, and at in the end only. You know that the boxes are in the end only, but it could be in the first row, it could be in the second row, it could be in the third row, whatever you got. So at this point, what you need to, the rightmost will work. Okay, so that was the in the notes also. So for example, at this point, this is your 5, this is your 5. Now you know that the fifth row number will be in the next from the other side. So but which one you need to consider? So what you will do, like this is a theorem for that. Yeah, if A is less than or equal to B and P is your SSYT, like semi standard Young tableau, and P has been inserted with A, and and P2 is P1 has been inserted by B, then the new cell of P1 lies in row I and column J. So what you are saying, okay, then J dash is greater than J, and I dash is less than or equal to I. So what we are saying, you have some Young tableau, I don't know exactly anything, kuch bhi. Okay, anything you consider. This is your, for example, P, and for example, A has been inserted and B has been inserted to P1. So for example, A has been inserted here. So let's say this is your A. I'm not saying this is the exact position, anything, I just considered anything. And for example, this is your B. So after A, P has been inserted. Then the new cell of P1 lies in row I. Let's say P1, the new cell of P1, that is this is row I, that is second row, and column is third column. Okay, this is I comma J, and P2 lies in row I dash, that is your 5, and column J dash is 1. So this is I dash and J dash. Then the relation between I dash, J dash, and I and J, the relation will be what? Relation will be, then J dash is greater than J. J dash is greater than J means this is J dash is 1, and J is 3. So this cannot be the possibility. Okay, what we are saying, J dash should be greater than but here you can see J dash is 1, so this cannot be a possibility. So that means what we are saying, this should be reverse, like this should be, so basically the rightmost one will be important, like in the column term. So column should be bigger. Okay, the column number should be higher than uh, higher in the later one. Okay, so when we inserted p1 b in p1, that is the later one. The earlier the a has been, so you have p, you have inserted a, and then in that, so let's call it p1, and then in p1 you have inserted b, so the later one is b and the earlier one is a. So we are saying when we insert B, B should be in the rightmost column, like compared to the previous one. Okay, this should be in the right column. Like right means the column number should be bigger than A. Is that clear?
Yes, ma'am.
So if you have such type of condition, then this one must be the last one, like which you have inserted later. So you will consider this one. So because you are going from right to left, so you need to consider the next one, like the last, the whichever the number has been inserted latest, that you need to consider. Okay, so this is not the case here, but this could come in the questions maybe. Okay, so you got A up to the rows 0 and 0 rows or 0 columns in the end. Okay, if you have given the size, then definitely there's no issue. Okay, so let's move to the next question. Find S lambda. You need to find out the S lambda, and lambda is 2 comma 2. So these are some questions which are related to how you can write Schur polynomial in terms of monomial symmetric polynomials, right? And we did some questions last time also related to that. Okay, let's do it. So lambda is given to be 2 comma 2. You need to find out what is S lambda in terms of in terms of monomial symmetric polynomials. So how we do that? Can you tell me the formula?
X.
For example, I write mu. So what should be the coefficient?
CF alpha
Cos का polynomial?
alpha mu lambda.
Yeah. Lambda mu. So whatever be the shape, you will write it first. So that is your shape and this is your mu. So mu is equal to P. Now n is not given, so we assume that this is big enough. So we are not writing it. So P, and so whatever lambda is 2 plus 2. So lambda belongs to the partition of 4. So you will consider mu belongs to partition of 4. Okay. Now, so what we need to figure out, we need to find out this value k lambda mu for various mu's. So mu is given to be what? Mu belongs to the partition of 4. So what partitions we can have for 4? So 4, yeah, you can consider. Can you tell me the partitions of 4?
4 1 3.
Yeah,
2
3 1 2 2 plus
1.
Yeah, the best way to write it in a pattern, so as I usually write, so you start with the biggest number that you can have, that is exactly that number. Okay, so you have 4. Now you go one number down, so you start with 3. Now you will get 1, right? So 3 plus 1, so you write, so first you go one number down, like 4, and then you take one number strictly less than 4, that is 3, and you write the extra number as plus 1 or whatever it is. Now there is no other option. With 3 there is no other option, right? So you go one number down again, that is 2. Now
plus
2. No, first write the whatever you got, got as the, when you subtract this, you got 2, right?
2.
2 plus 2. Now you with 2 only, you can have the, now you do the partition of 2, that is 1 plus 1. You can have multiple partitions, okay? So that you need to do. So this is recursive. Now now you go down by now you start with 1 because there is no other option for 2. So now you go down by 1, so you get 1. And now you know that you are writing in the decreasing order. So when you subtract it, you cannot write 3 because 3 plus 1 has already been considered. So you are considering the pattern of pattern to be uh, weekly decreasing. So this is weekly decreasing. So you start with 1, so 2, when you go down by 1 you will get 3. Now you cannot write 3, you can only have 1 or less than 1. So you can have 1 plus 1 plus 1. So these are all you can have. Is that clear?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. So you have these 5 partitions. So mu could be anything because we have no control on x size, because if x size is just x1, x2 and x3, then you would have to consider this much only. Like for the last one, you cannot consider that part, because for that you need x1, x2, x3 and x4, right? So as we usually write 4 comma whatever n is, but here n is not given. That means we are in a good situation that n is big enough. N is bigger than this t. Okay. So yeah, so let's try to find k lambda mu for all mu belongs to, that we need to find out. So let's start with 4. Okay. So k lambda is given to be 2 comma 2, and mu is 4. So what exactly you have, so this is a way we write the partition. So you have k 2 comma 2 and this is 4. So this is your shape and this is the type. So shape says you consider 2 comma 2, that means this and this, right? This is the shape. Now you will consider the type. Type says type is 4, that means you have 4 ones, right? If you remember, this is how we find k lambda mu. So you consider whatever type is given, you will consider the first letter to be, first number will tell you how many ones are there, second place will tell you how many twos are there, and so on. So you have 4 ones right now, so you can have 1 at all the places. You can only have 1 because there are 4 ones. But is it a tableau, semi standard tableau?
Yes, ma'am.
Is it?
No, ma'am. Only one.
Only 1 means
This is wrong because that column wise is not strictly.
yeah, exactly, very good. So column wise it should be increasing, strictly increasing. Okay. So this is not a possibility, so this is not a tableau. Now so this is 0, so k22 comma 4 is 0. Now you consider the next one, which is 3 comma 1. So for that again the same, you have the tableau to be just this. Now you have to put 3 comma 1. So 3 ones are there and 1 twos are there. So
This
3,
is also possible.
sorry.
This is also not possible,
Yeah,
ma'am,
exactly.
because 1 and 2
Yeah.
first column is not
Yeah.
strictly.
So this is the only possibility, and that is even again not a tableau. So SSYT, no. Okay. So next, this is 2 comma 2. So this is the same. So you have two ones and 2 twos. Yeah. You'll get? You can tell me?
Yes, ma'am.
Yeah.
1, 2, 2, 2, 3.
2 2, because 2 twos are there and 2 ones are there.
Yes, ma'am.
So, and you can always see, like, if you have k, lambda and mu are the same partitions, then you'll get exactly 1, because there is no other option. You will write the first row to be that number, the second row will be the next number, third row will be the third number. So these are the only options. So you'll always get this to be 1 if these are same, and this is 0. Let's see the next one. You have 2 1 1. So 2 1s are there, 1 2s are there, and 1 3s are there.
1 1 2 3.
1 1 2 3. Right. Very good. And there is no other possibility, right?
Yes.
So this is 1. Next.
1 1 2 3 4.
Yeah, 1 1 1 1. Yeah, 1. Oh, right. How many will be there?
1 2 3 4, ma'am. 1 1s, 1 2s, 1 3s, 1 4s, 1
Yeah.
2 3 4.
1 2 3 4. Is there any other possibility?
No, ma'am.
No. There's one option, if you see.
1 3 2 4.
Right. So 4 will be in the end, because there is no other option. 1 will be in the first square. So the only option for 2 3 could be switched, and that is a possibility, because increasing, there's no issue, right?
Yes, ma'am.
So these are 2. So what exactly you got from this? S sure polynomial 2 comma 2 is equal to, so zeros we will not consider. For this we have k22, so you'll get m. Now I'll write in terms of m only. So 2 means m22 you get. Next m, so again this is 1, which is m211. So you'll write mu, because the mu number you will write, and the coefficient here is the Koska number. Next you get 2, and you will get 1 1 1 1. So this is your answer, right? 2 1 1. These are only possibilities. Is that okay?
Yes, ma'am.
Okay. Okay, let's see the next question then. Find the coefficient of x1 square, x3 square, x5 square in S411. So basically you need to find out, not find out 411, you need to find out the coefficient of this. Okay, so there are ways to think of this thing, like there are ways, as in so you know that I better write small s for sure polynomial. So you know that what this will be. There are ways to write in the form of k lambda mu and m mu, and mu is some partition. Okay, here partition is what? 4 1 1, that is 6. Again yeah, x5 is given, but doesn't matter right now. So we assume that, because there is no explicitly there is no limit written, but we don't care, because we just need the coefficient of this number. Okay, let's see. Yeah, we assume that this is big enough, n is big enough. Or maybe just say n is greater than 6 or equal to 6. Okay, because otherwise the number might be here. Okay, because for example, if n is equal to 5, then this is a symmetric polynomial, so there must be something x1 square, x3 square, and x6 square. Oh wait, no, it's fine. Okay, doesn't matter. Doesn't matter, right? Because the partition, so for example, if n is 5, then you will have all the permutations in these numbers from 1 to 5 only, so there is no issue. Okay, so but yeah, for example, here we don't care about n. So what we need the coefficient here. Okay, so mu belongs to p6 and k lambda mu we need to figure out. This is the Koska-Poly number, and mu we know. So what exactly this is one way to find out. The other way is, you know, that you take the summation over, I'll write type t, and what is this? You consider all the shall I write all the fillings, or maybe, yeah, SSYT tableau. So SSYT, semi standard young tableau, with fillings 1 2 3 up to and so on n. Okay, that is other way. So t belongs to this. T is a type. This is not a SSYT of type T, that is with fillings this. Okay, so you need to find the type. Type means type says so when we fill it, we will fill it using 1 2 3 4, and the number the number of times 1 will be repeated, that will be your first entry in the type. So for example, if you have something like this, let's say you have this 1 2 not so let's say you have 2 3 4 5. For example, if you have this, then the type you will get 1 has been repeated 2 times, 2 has been repeated 2 times, 3 has been repeated 1 time, 4 has been repeated once, and 5 has been repeated once. So this is your type, and corresponding to that you will get x1 square, x2 square, x3, x4, and x5. So this is the number you will get here. This is the monomial you will get here. Okay, so what you need to find out? You need to find out the coefficient of this element, x1 square, x2 square, sorry, x3 square, x5 square. There's one more thing I'm confused. Oh right, yeah. So with these numbers itself, you can get so what I want to say, if you consider this type, you may have many you may have more than one so this is exactly, think about it. So you have this type, this is your mu. Okay, and when you have mu and lambda, so basically you need to find out the Koska polynomial corresponding to this type, right? So what I want to say, ignore this, for example, not ignore, like think about in our question, the coefficient has been asked for this polynomial, for this monomial. So the corresponding type you will get, type is, can you tell me what will be the type? So type will say, type says whatever number is like the first will be the number, the position, and then you have 2
Two types of 2,
2
comma 2, comma
0
2.
0 0, because x2 is not here. So 2 0 2
So,
0 2. Okay,
yes, ma'am.
okay, you got this. This is your type. Now corresponding to this type, you need to and so this is for example your mu, and lambda is given to be what, 411. So what you need, you consider the tableau. So 411 is your shape. So shape means you consider 4 blocks, and then you have just one block, and then next you have just one block. This is lambda. Now you need to insert these 2 ones, 2 threes, and 2 5, right? So
Yes, ma'am.
so you need to insert these numbers. Let's see how can we do that. So you have two ones, that means one must be started here only, and it cannot go in the second row because that should be strictly increasing, so 1 1 will be here. Now you have two threes, so 3 1 can be here, the next one has to be here because you cannot go in the next one. Now you have 2 5, so there are 5, so this is the only possibility, right?
Yes, ma'am.
There is no other way. So for example, yeah, if you have just like 1 1, then you might have you would have get 2, but okay, in this question there is just 1, sorry. So you got this. So the coefficient of x1 square, x3 square, x5 square in the sure polynomial 411 is 1, right? Because corresponding to this type, how many numbers you will, with fillings, that how many numbers you will get, that you will write exactly here. Okay, one more thing, there should be some coefficient thing, no? Let me see once. Yeah, this is the same thing, like I'm just saying how exactly it has been written in terms of formula. That is something I just want to confirm. So SSYT shape lambda fillings with this. Okay, T belongs to T belongs to the shape. Yeah. So this is the shape corresponding to the shape of So T belongs to SSYT with the shape lambda. Lambda is here, this. Okay. So yeah, how many tableau you can get, that is the point. Because this is just considering the type. So with different T, you can get the same type. That's the major point. Is that clear? Okay. Okay. Okay, let's move to the next question then. Are the following power series symmetric functions in infinitely many variables? Okay. So yeah. So okay. So in infinitely many variables, so we consider okay. So if you have seen the lecture notes, so power series could be anything. It could be infinite sum. It could be like, it doesn't matter. But when we talk about the infinitely many variables, there are some restrictions, and there's a symmetric thing we need to check also. So let's see what I want to say. Here you have I is equal to 1 to infinity x to y. Is it can you tell? So to okay, for a power series to be a symmetric function in infinitely many variables, the following must be not checked. For a power series to be a symmetric function, it must be satisfied. The following conditions must be satisfied. So what are those? Actually this is not okay, symmetric is always homogeneous, that you can easily see. So as I'm saying symmetric, so this is anyway homogeneous. Oh, sorry. If it is a power sum, then it has to be symmetric. Sorry, it has to be homogeneous. But let me add this term also. Doesn't matter, but still I want to consider homogeneous. Okay, it could be a sum of, for example, it could be m2 comma 1 plus m3 comma 1. Okay, this is also possible as symmetric function, but this is not homogeneous because the powers will be 3 and here the powers will be 4. So you have some sum. So for homogeneity we need all the terms have the same power. Okay, so I am concerned about right now homogeneity, but there is no issue there. It's okay if we just consider symmetric functions. And yeah, but the given polynomials is the given polynomials are homogeneous, so it's fine to consider homogeneity also. So first is again all the terms have the same degree. Same degree. Okay, this is mixed degree. Mixed degree means the total degree. Total means all the so the you consider the term, for example, x1 x3 x5 square. So the total degree is this 2 plus 1 plus 1. Okay, so same total degree. Second condition says, yeah, second condition says that if you have for example okay, if you have x, okay, xi means I mean if you have xi, then you must have x sigma I. What does that mean? For example, if you have x1 x2 x3, then you must have sigma of this I means, let me write lambda. Lambda is better. So lambda is 1 2 and 3. So where it goes, that is the main thing. So sigma of 1 2 3 and up to and so on. Okay, so sigma of lambda, if lambda is equal to 1 2 3, okay, or maybe we can write it as a set. Oh, it's fine, you need to write it in a order. Okay, now what is this sigma? Sigma belongs to automorphism of n, or maybe if you want to write permutations of n. So what does that mean? It is not restricted to just finite number because we are in the infinite variable situation. So infinite variable means sigma should also be should be permuting in that infinite set. So what we are saying, we will move to, so it starts with 0. So are we allowing 0? So I'm writing n plus because we are not allowing 0 right now. Okay, so sigma belongs to permutation of n plus, infinitely many variables, and we are talking about n plus. Okay, so or maybe I can write p. So this is 1 2 3 up to and so on. The other side you have 1 2 3 up to and so on. So there should be a permutation. So permutation means automorphism between the set p to p. Okay, so you must have, if you have x1 x2 x3, that means all the permutation should be there. So x1 x2 x3 means now one could go to any other number. Let's say 1 can go to 3, 3 can go to 5, let's say 5, and let's say 2 can go to anything, let's say 6. So you must have x3, x5, x6, you must have all the permutations. Okay, so that means 1 2 3 could be replaced by any other number, any distinct three numbers out of these positive integers. So that means if something has to be a symmetric polynomial, then the coefficient, oh right, I should write it as coefficient, c of lambda should be same as c of sigma lambda. So because when you permute it, you should have the same coefficient, so that the polynomial will not, when you, so what is the requirement for a symmetric polynomial? F of x1 x2 up to and so on should be same as x sigma 1 x sigma 2 up to and so on, right? So if you permute your n, then you must have the same polynomial where you have started. So that is the symmetric thing which we require. Is that clear? Or yeah, I should not write polynomial, because polynomial usually is finite, or power series, symmetric power series or symmetric function can be a possibility. Okay, so these two conditions should be there. Now can you tell me if this is a power series with is a homogeneous symmetric function, this one? So note that what is this? This is equal to, I'll change color. So this is equal to, I goes from 1 to infinity. So this is multiple of 2. So it just says x2, x4, x6 up to and so on, right? So these are just even things we are getting. Can you tell me, is this a symmetric function or not?
No, ma'am. I think.
Reason? Yeah, yeah, the answer is no. Can you tell me the reason exactly?
Symmetric function homogeneous means finite.
Okay, just think about, as I said, what you need to have. Condition says c lambda should be same as c lambda sigma lambda, means if you have, for example, this 2 is given. So if you consider a permutation from n to n or n plus, then 2 can go to somewhere. For example, 2 can go to 1. So you have a permutation where 1 2, we don't care where 1 goes, where 3 goes, we don't care. But where 2 goes, for example here in this condition, so 2 goes to 1, then condition says c lambda, c, these are coefficients of corresponding lambda. Okay, coefficient of x lambda means whatever lambda is, like lambda, let's say 1 2 4, then it will be x1 x2. I'm not writing in an exact way, but yeah, it's something wrong, like, or maybe you write x lambda 1 x lambda 2, something like that, because there could be powers also. Oh, right, lambda better be right like this. So lambda is equal to, for example, 1, so this will tell you the powers, so 1 1 1 0 0 0 up to and so on. So this corresponds to this. First entry will tell you the power of x1, second entry will tell you the power of x2, third entry will tell you the power of x3, fourth entry will tell you the power of x4, and so on. So right now it's just 1 1 1. Okay, is that clear?
Yes, ma'am.
So this is your lambda. Now we are saying you apply sigma. So not on this, you apply sigma on this. Okay, yeah, that is something I'm not writing it clearly. Sigma on, yeah, it's fine. You apply on lambda because these are the positions. So what you are saying, when you apply sigma, and sigma belongs to what? Sigma is a permutation of n plus. So what it should do, this will tell you, so you should have all the possibility, like 1 0 0 0 and then 1 1, so, and 0 0 0 0. So 3 ones could be anywhere on this line, on this n line. So that means you should have, for example, x2 x5 x6 x2 x4 x8, you should have here at these places you can have any three distinct numbers. That is the main thing. Okay, so the coefficient should be same. That means if this is 1, the coefficient is 1, then you must have for the coefficient for this also should be 1, and any three numbers which are distinct you are considering. Okay, so at this place, so this 2 is given, so you must have x1 also, because 2 can go to 1. So if you want to write it as a type, so for x2 is what, the coefficient is 1. Okay, and x2 can be written in the form of, you have the corresponding, this is, okay, right, and this can be permuted. When you apply sigma, you can have 1 0 0 0, right? Then the coefficient should be same, and the coefficient for this is 1, so you must have, this corresponds to x1, so you must have 1 into x1, but that is not here, right?
Yes, ma'am.
So you should have all the permutations. Just think about, we normally do in finiteness, but we are saying we allow everything. We can permute in any like in any number of variables. So this is not a homogeneous symmetric function. Now what about b? So you have this summation I is equal to 1 to infinity x2i plus summation x2j minus I. Now what exactly is this? This summation says x2 plus x4, tell me, and up to and so on. And the other one is?
X1, X3.
Yeah, so this is exactly the full, you can write it summation x, if you want to write it in terms of k is equal to 1 to infinity. This is this. Now can you tell me if this is a symmetric function or not? If this is a symmetric function, this one, summation, so I can write it here, summation xk, k is equal to 1 to infinity. Is this a symmetric function?
Yes.
Yes, no? Because what you need now, you have some xk. Now corresponding to that, the coefficient is 1, right? Now we need for every permutation you should have some the coefficient to be 1, and you know that xk can go to any xk dash. Xk will go to any xk dash under sigma, and you have that because this is the whole sum. K dash could be anything. Okay, k dash belongs to any n plus, right?
Yes, ma'am.
So this is okay, this is a symmetric polynomial. And one more thing, you cannot have in these things, the term cannot exceed, the term cannot go infinity. Like for example, you cannot have something like the term itself to be multiples plus something something, you have for example x2 square x3 dot dot dot. So I'm saying the product cannot be infinite product, that we are not allowing for symmetric polynomials, sorry, symmetric functions in this power series thing. Okay, the product cannot be infinite, that we should remember, because that does not explain anything, that we cannot define in any other term, like, yeah. Okay.
Yes, ma'am.
Okay, so yeah, let's move to the last question. So the symmetric function s5 comma 1 is equal to the determinant of what? Determinant of which matrix? Okay. So this is related to that explanation by LGV lemma. So the solution I can recall. So you have this, yeah, this one. Now, so theorem says this: H is, if lambda is lambda 1 greater than, so you have this decreasing, weakly decreasing sequence. H is L cross L matrix whose ijth entry is H lambda I minus I plus J. So I'll just collect it. So H is this matrix. First thing, I'll copy here first and then oh, what is this? Okay. Anyway, okay, the lines will be selected only. Okay, no problem. So what I want to say, so this is H is, if you have given lambda to be of this kind, and then H is a L cross L matrix whose ijth entry is H lambda. H is your homogeneous polynomials, homogeneous symmetric polynomials, H lambda I minus j plus j x1 up to and so on xn. And the theorem says the S, the Schur polynomial, or here, then the Schur polynomial with the shape lambda is equal to determinant of H, and also determinant of E. Okay, so this is the result we are using. So Schur polynomial is a determinant of H. Okay, and what is H? So you need to find out what H we are talking about here. So matrix H with the entries, ijth entries, H lambda I minus I plus j. Okay, let's write it here. So we are saying S 5 comma 1, let's say this is, or maybe I'll write in general right now, lambda 1, lambda 2 up to and so on. This is the determinant of matrix, or maybe I'll write determinant of matrix H with ijth entry as entry S. So you have sorry, again, ijth entry is H lambda I minus I plus j. Okay, so this is the entry, and yeah, the homogeneous polynomial is the entry, and xn. Okay, so yeah, this is the determinant we're talking about. Now this H, what is H? So let's see in our case, S is, so lambda 1 is given to be what? Lambda 1 is, yeah, lambda 1 is 5 and lambda 2 is 1. Okay, 1 second. So lambda 1 is 5 and lambda 2 is 1. Now what we need to do, determinant of matrix H. So what is, okay, in the determinant we are just concerned about the two rows, because the third entry is 0. So lambda 1 is non-zero, lambda 2 is non-zero, lambda 3 is 0. So and later on it is just 0. So we just need to think about that. So we can think of this is just with x2. Okay, because as you see this is okay, just L cross L matrix such that the last entry is non-zero. Okay, lambda L is non-zero, so you will just consider 2 cross 2. So this is 1, and so 2 cross 2 matrix you are considering. Now what is the entry? Lambda I, so for first, so we need to first find out the entry 1 comma 1. Lambda 1 is what? Lambda 1 is 5. So H lambda 1 minus 1 plus j is 1. So this will be just H lambda 1. So lambda 1 is just 5. Okay. Next, H lambda, so again the entry we are talking about here 1 comma 1. Next entry, or maybe if you want to write, okay, this might confuse, so it's just okay, 1 comma 1, so 1 1 entry. Second entry 1 comma 2, this entry you will get 1 minus, so I is 1 and j is 2, so you'll get H lambda 1 plus 1, so you will get H6, right? Okay, and 2 comma 1 1th entry you'll get this minus 2 plus 1, you'll get H lambda 2 minus 1. What is lambda 2? Lambda 2 is 1. So this is 1 minus 1, that is 0. And that is 1 we consider as definition. So h0. And now 2 comma 2th entry. So lambda 2 minus 2 plus 2, this is h lambda 2, this is 1. So you will get h1, right? So h5, h6, h0, h1. Let's see which one is it. H5, h1, h0, h6. This is the one. So actually there is a pattern here. So pattern means nothing of that kind. So what you, if you observe in the, on the diagonal side, you know that I and j are equal. So on the diagonal, it this part will be just 0. This I and j are same. So this will be 0. So you will just get h lambda 1, h lambda 2, h lambda 3. So you will get on the diagonal h lambdas, okay, corresponding to the place. And now on the right side, so if you consider for example this, on the right side you just increase it. So with 5 you increase like 1, because what you are doing, I is fixed, now j is in sum. So you, when you move along the column, along the number of column, sorry, yeah, so you have first column, second column, third column, but the row is fixed, so you are just adding plus 1. So h5 you will next get, so if you start with h5 you will get h6. If there is any other row column, then it will be h7, and so on, if it is like that. And for example here you will get h1. And now if you observe in the second, in the row again, on the right side you will just add the thing, because row number is fixed and column number is just increasing by 1. So this is h3, h2. And on the left, when you consider this, on the left what is happening, row is the column, sorry, the row number is fixed but column is decreasing by 1. So what you will do, on the left you will just go down like h0. If there is like h minus 1 is not something which we deal. So so if there is like for example this is h2, then this is h1, this is h0. So you can write it directly, like not, it's just something which you can observe from the entries itself. Is that clear?
Yes, ma'am.
Okay.